today we are going to learn chapter 5, linear second order equations, and 5.1, homogeneous linear equations. So we learned what is the homogeneous linear equations, right? So other side equal to 0. So the equation is 0, right? So we had linear first order differential equations. So the form is like this, right? So y prime differential derivative, right? And plus the polynomial y equal to times y equal to f of x. So in that case, f of x is a constant 0, right? So other side equal to 0, so we called homogeneous equation, okay? This chapter, we have linear second order differential equations. So we have a second derivative, then decreasing derivative, then we have polynomial first derivative, right? And we have another polynomial. We just using different notation, q of x, p of x, q of x. But we can use any letter, right? Any variable. Then just y equal to f of x. Yeah. And if we want to express this one as a homogeneous equation, then f of x must be equal to 0, right? So we have homogeneous equation. All right. Okay, now we have a theta. So this is second linear second order homogeneous equation, right? So y second prime plus p of x times y prime plus q of x times y equal to 0 with initial value problem. Look, normally we have initial value only one in the linear first order differential equation, right? But then since we have a second linear second order differential equation, we have two different initial value. Yeah. This one, we've seen this one before many times, right? But then this is a brand new. This is another initial value problem. Y prime of x naught equal to other constant. Yeah. Because this one has a linear second order. That's why we need another initial value in order to solve the problem, okay? And then they said that has unique solutions. There is only one solution, right? Unique solution means, yeah? Okay, so let us do this example so that we find the solution, unique solution, okay? All right, so we have x squared y second prime plus xy prime minus 4y equal to 0, differential equation, homogeneous equation, right? And then we have two initial, yeah? Oh, in that case, we have three polynomial. Because I don't see that the prime initial. Okay, so one is polynomial x squared. Second one is x. Third one is -4. Has unique solution on only positive part, right? 0 to positive infinity. Yeah. So x naught is greater than 0 means only positive. And then negative part, right? Then we have verified that y sub 1 equal to x squared is a solution of everywhere, right? Negative infinity to positive infinity. And y sub 2 equal to 1 over x squared is a solution on, we don't include 0 there. That means, right? So negative part and positive part. Yeah. Okay, so we have a p sub 0 p naught x squared will be this one, right? And then p sub 1, which is x here, p sub 2, which is negative 4 in the polynomials indicated, right? And then there is no initial problems here, initial value. Yeah? Okay, so we have two solutions. So we have to check it out. Yeah? So y sub 1 equal to x squared first. Then let me bring the form of second linear second order differential equation, right? So let me have this one here. Theta, copy, paste, and then make smaller, and then uh, just like that. Yeah? No? Okay. Oh, sorry. Okay, maybe last chance. Yeah. Okay. Uh, let me write down. So we have y second prime plus p over x, y prime plus q over x, y equal to 0, right? Okay. Then let y sub 1, it's a given x squared, right? So we have here, right? Y sub 1 equal to x squared. All right, then the original question we have x squared y second prime y second prime plus x y prime minus 4y equal to 0, right? Okay, now y sub 1's first prime, what do you get? We get 2x. What about y second prime? The y sub 1, y second prime. We have a 2. Very good, right? Okay, then we have, hold on one second, x squared, right? So we substitute y second prime, 2 into y second prime, 2x into y prime. Yeah? Okay. So let us do that. So we have x squared, y second prime, which is 2, plus x, y prime, which is 2x, and minus 4y, which is x squared, yeah? And equal to 0. So basically, we substitute everything, sub 1, sub 1, sub 1, right? Make sense? From the original formula to here, right? Okay, now simplify. So we have 2x squared, let me use the same color. 2x squared plus 2x to the second power minus 4x squared equal to 0. Yeah, this is a true statement because 0 equal to 0, right? 0 equal to 0. So we can say that y sub 1 equal to x squared is a solution for everywhere, right? Okay. Now we understand what we are doing, right? So let us do second solution, which is y sub 2 equal to 1 over x squared, right? Okay, so we have let y sub 2 equal to 1 over x squared. Okay, so we have the formula x squared y second prime plus x y prime minus 4 y equal to 0. In that case, second, right? For the subscription. All right, then y sub 2 prime. We want a derivative. So there will be x to the negative second power, right? So we should have the power reduced by 1. So x to the negative third. So there will be negative 2 over x to the third power, right? What about the x sub 2 second derivative, right? Okay, once again, this will be negative 2 x to the negative third. So we have negative 2, negative 3, and x to the reduced by 1. So we have a negative 4, which is positive 6 over x to the fourth power, right? Okay, let's substitute. Yeah. So we have x squared y second prime 6 over x to the fourth power. Oops. Oops. And let's see, plus x first prime. So we have negative 2 over x to the third power, right? And minus 4, just y, which is 1 over x squared. Oops, I'm I have to, yeah, substitute, yeah. Okay, so we have a plus x minus 4 equal to 0, right? Yeah, proper one is the substitute. Okay, let's simplify. We have 6 over x to the second power minus 2 and x to the second power minus 4x squared equal to 0. Yes, right? So that is 0 equal to 0. Yeah, that is a true statement. So we say that y sub 2 equal to 1 over x squared is solution for x and not include 0, right? In negative infinity, positive, no, 0, union of 0 and positive infinity, right? Okay, you can see the green, right? Yeah. Okay, very good. All right. We have a terminology linear combination we learn from linear algebra, right? That's why differential equation prerequisite is, I think, calculus 3 and linear algebra, right? Okay, so we have linear combination. Okay, so linear combination, the form is y equal to c sub 1, y sub 1 plus c sub 2, y sub 2. This is a form of, right? So we can use any variable, right? We say that this is a linear combination of y sub 1 and y sub 2, right? So for example, if we have y equal to 2 cosine x plus 7 sine x is linear combination of y sub 1 and y sub 2. this is a y sub 1 cosine x. Y sub 2 is sine x, right? And then constant. We call it coefficient, right? So C sub, because the number in front of the function, right? So 2, 7 there, right? Okay. All right. Now, we have theta, y second prime, which is, this is a linear second order differential equation with homogeneous equation, right? And linear combination form, which is, we just had a y equal to c sub 1, y sub 1 plus c sub 2, y sub 2 of y sub 1 and y sub 2. We said that linear combination of y sub 1, y sub 2, right? Then we say that y sub 1 and y sub 2 is also solution of homogeneous equation. Yeah. Okay, let me prove. All right. Okay, let me prove this theorem. All right. Okay, so let's prove. So we have, let y equal to c sub 1, y sub 1 plus c sub 2, y sub 2, right? Okay, now derivative of first prime, then c sub 1, y sub 1 prime plus c sub 2, y sub 2 prime, right? Okay, what about the second prime? Y sub second prime will be c sub 1, y sub 1 second prime plus c sub 2, y sub 2 second prime, right? Okay, now we have the homogeneous equation, right? So I want to copy this one, left side, copy, paste, right? All right, we have that. Okay, now I want to make more page. All right, so if we have that, then look, I want to substitute y second prime with this, y first prime with that. Yeah, okay, let's do it. So second prime will be c sub 1, y sub 1, second prime plus c sub 2, y sub 2, second prime plus p of x, y first prime, which is c sub 1, y sub 1, first prime plus c sub 2, y sub 2 prime plus q sub x, y, but y in the case, that one, right? So, okay, I need more space. I need to make a little bit smaller, yeah? Okay, now I can substitute y. Y will be c sub 1, y sub 1 plus c sub 2, y sub 2, right? Okay, now let's arrange y sub 1, y sub 1, y sub 1. Yeah. Then y sub 2, y sub 2, y sub 2. All right? All right, so that will be uh, equal to, so c sub 1, y sub 1, second prime, plus p over x, c sub 1, y sub 1 prime, plus q of x, c sub 1, y sub 1. Yeah, okay. Then second term, y sub 2, right? Plus, and c sub 2, y sub 2, second prime, plus C sub 2 y sub 2 prime plus C sub 2 y sub 2. Yeah. Okay, now they have a common denominator, not denominator, common factor C sub 1. So let us do that. So C sub 1 and y sub 1 second prime plus p of x, C sub 1, y sub 1 first prime, q of x, C sub 1, y sub 1, right? Okay, now we have common factor will be C sub 2, right? So there will be plus C sub 2 y sub 2 second prime plus C sub 2, C sub 2, we factor out, y sub 2 prime plus C and y sub 2, right? Okay, missing, looks like missing something. Let me check. Okay, so I made a mistake there. Sorry about that. So we have a p of x times y prime, right? So y prime and we plug in, right? So it must be p of x of, right? Whole thing. And also q of x of whole thing, right? Okay, then let me fix that. So that will be, oops, p of x. So we make 2, right? So so p of x, c sub 2, y sub 2 prime, and this will be yeah, I can just say q of x, yeah, but it's okay. Too late. So that will be q of x and c sub 2, y sub 2, right? Okay, now we have, yeah. And then I made another mistake there, C sub 1. Yeah, why didn't you tell me? Yeah, so you did not tell me, so I make a mistake. Okay, so we have P of X here. We have Q of X there, right? Q of X there. Okay, then look. This one, we've seen this one before, right? Yeah. So they said in the beginning we have this form is a homogeneous equation, right? So let me copy down this one. We have, right? So we can say that this one equal to 0, this one equal to 0 because homogeneous equation, right? Yeah. Okay. Then we can conclude there will be C sub 1 times 0 plus C sub 2 times 0, right? Okay, then we times 0, then every term is 0, right? Yeah. So look, we start with linear combination and then we substitute into the homogeneous equation, right? Still, we get the homogeneous equation, so it works. So we say that the linear combination of y sub 1, y sub 2 is also solution of homogeneous equation. All right, so let me write down. All right, so I wrote down here for conclusion. Okay, let's move on. So we have a linearly independent. Everything is come from the linear algebra, right? So linearly independent, y sub 1, y sub 2 are linearly independent if neither is constant multiple of the other, and if there is trivial solutions. So if the non-linearly independent, we say the linearly dependent, right? So we can express constant multiple of the other, y sub 1 equal to c times y sub 2, right? So we called this is linearly dependent, or we can express y sub 2 equal to c times y sub 1, right? So I said vice versa means we can express this one or we can express this one, right? So we can switch over y sub 1, y sub 2, right? So we call this is constant multiple of the other. So linearly dependent. Also, if we have trivial solution, that's also linearly dependent, right? Yeah. The answer equal to 0. That's a trivial solution. Yeah. Okay, now, okay, so I want to bring up previous linearly independent, right? So we have, I want to make sure y sub 1, y sub 2 are linearly independent. Okay, we cannot express as constant multiple of the other, right? We call this is linearly dependent, but I want to make sure understand this one. If we have a trivial solution, then we say the linearly dependent. Yeah. Okay. Now, we had a expression about the linear combination earlier, right? Then at the time, y sub 1, y sub 2 is also solution of the homogeneous equation of differential equation, right? So in that case, we have if, only if. This means if, only if and only if. That means going this way make a true statement, and going to this make a true statement, right? Yeah, we learned this one from previous courses, right? Okay, so homogeneous equation, differential equation, that is a linear second order, right? And then y sub 1, y sub 2 also, not also, is linearly independent, right? So think about trivial solution. Okay, now we have a lot of concepts here. Okay, we have a second linear differential equation here, right? And then we have initial value, which is initial problem here. Now we can express as linear combination. This is a linear combination. Yeah. Okay, then has a solution C sub 1, C sub 2 for K sub 1, K sub 1. Sorry, K naught and K sub 1. Okay? All right, now we have da da da. This section is about the Wronskian. Yeah. Okay, let's take a look. So we have linear second order differential equation and homogeneous equation, right? Okay, so we have a Wronskian. We're using first letter W. Yeah, in that case, W. All right, then We have a determinant. Then we multiply this way, right? Diagonally, 2 by 2 determinant. Yeah, let me write down. Think 2 by 2 determinant. Okay, then we multiply this way times minus, we multiply this way, right? Diagonally, right? Okay, so in that case, we have y sub 1 times y sub 2 prime and y sub 2 times y sub 1 prime. So the order is like that, right? So y sub 1, first column, and y sub 2, second column. Yeah. Okay, now how do you solve for c? C sub 1, 1 over, we have x naught, we plug into Wronskian, and then we have k sub naught, k sub 0, k sub 1, and y sub 2, x naught, y sub 2 prime x naught, right? And we make a determinant here again, yeah. And we moved, can you see that? This one come back to the second column, and oh, it's a different one, yeah. We are using k sub k naught, k sub 1. We have a second column, y sub 2. Makes sense, right? And then we have y sub 1 for the first column, and then k naught, k sub 1 move to the second column. Okay, do you remember moving the column? Did you see somewhere before? Yeah, right. So in the linear algebra, Cramer's rule, right? Yeah. So they change the column, right? Yeah. Okay. All right. Then we have another concept, Abel's formula, but we're not gonna use it. We just have Wronskian, right? Wronskian, right? Wronskian. Yeah. Okay. So we have Abel's formula like that, right? So e to the negative integral of from x naught to x, p of t dt, right? Okay, so therefore, either w, the Wronskian, has no zero in AB, or Wronskian equal to zero on AB, yeah? So zero, this means identically zero. Okay, I wrote down here the concept. So Abel's formula tells exactly how the Wronskian change with x. What this means, change with x. So this means Wronskian is a function of x because we input the x there, right? Yeah. That is whether it stays constant, grows or shrinks as x changes. Yeah. Okay. So everything together. So Abel's formula tells how Wronskian behave. Yeah. So they behave at any point x or at one fixed point x naught. Yeah. Then they say that Wronskian is now equal to 0 at the fixed point x naught, right? Then whole Wronskian everywhere x is now equal to 0. Yeah. If the fixed one equal to 0, then everything equal to 0 as well. Okay? So knowing the Wronskian at one fixed point x naught completely determines the Wronskian everywhere else. Little bit make sense? All right, good. Okay, so let's find out what is Wronskian. Okay, so find the Wronskian we have given. Yeah. Okay, so I wrote down this one. So they're easily to calculate, right? All right, so let's do it. We have y sub 1, which is e to the x power, right? Y sub 2, we have e to the negative x power. And then we want to derivative y sub 1, derivative of e to the x, right? And derivative of e to the negative x, negative e to the negative x, yeah? Okay, determinant 2 by 2, so we multiply this way. So we get, yeah, they already have here, y sub 1, y sub, yeah, 2 prime. So we have e to the x times negative e to the negative x, yeah? This is the first time, so I am writing down for you, but later on we can just do directly, right? Okay, minus, we multiply this way, so same thing, right? So e to the negative x times e to the x, yeah? Okay, negative e to the x, let me write down for you, x minus e to the negative x plus x, yeah? Okay, now we get negative e to the 0 power minus e to the 0 power, right? Which is negative 1 minus 1, which is negative 2. Make sense? Okay, so second one, we want to find the Wronskian. Okay, so in that case, a little bit confusing. So they're using same, right? W. But this is not W, this is omega in Greek letter, like alphabet, right? So omega. Okay, now let's make the y sub 1, which is cosine omega x, y sub 2, which is sine omega x, and y sub 1 prime, which is cosine omega x, then times omega, right? And derivative of second one, sine, uh, oh my gosh, derivative of cosine. Yeah, I'm checking on you. So negative, right? Negative sine omega x and omega, right? Okay, now derivative of sine omega x. So we have cosine omega x omega, right? Okay, let's calculate. So we multiply. So there will be omega cosine square omega x, yeah? Minus, then we have negative omega sine square omega x, yeah? Okay, there will be omega, they have common, right? So omega is common. So cosine square omega x plus sine square omega x. Okay, so we notice that this is 1. So we get omega, yeah? All right. So this will be last question. So 2 solutions. And then I made a mistake here. Wronskian. Okay. All right, so first one. Y sub 1, negative 6 e to the negative 6t, right? Y sub 2, e to the negative 7t and negative 7, right? Okay, now, no, no, no. What I'm doing, just by itself. Crazy. Yeah. We're not derivative, right? Yeah. Okay. Now we do derivative, right? So we do derivative y sub 1 prime, so negative 6 e to the negative 6t, and second one, negative 7 e to the negative 7t, right? Okay, so we multiply, so we have a negative 7 e to the negative 6t and minus 70, right? We multiply other way, so negative positive 6 e to the negative 7t minus 6t, right? Okay, now we have a negative 7 e to the negative 13t plus 6 e to the negative 4. Wait a minute. It's yeah, 13, also 13, right? 13t, yeah. Okay, then what do you get? We get the negative e to the negative 13t, right? Okay, let's do the second part. Okay, so let's talk about the second part. Second part, find the solution with the initial value. So we have two initial value, right? Because we are doing linear second order, right? Okay, so in that case, this will be x naught and this will be k naught for the just the y equation, right? And from this solution, we call the solution. Yeah. And I mean the yeah, not solution, initial value, right? And y prime of 0, this one we called, yeah, x sub 1 is better, right? Yeah, x sub 1? Oh no, they're using x naught, yeah. The original statement using x naught, so this is x naught, yeah. So look, y of x naught equal to k naught and y prime of x naught equal to k sub 1. So just follow the statement, right? So this is a x naught as well. Same x naught, right? We have a 0, right? And this is a k sub 1, all right? Okay, now I brought the solution, I mean the formula here. Okay, so that we can find such as C sub 1 and C sub 2. Yeah? All right. So let's do it. So Wronskian, we have e to the negative 13t means 1 over e to the negative 13t, right? So C sub 1 over negative e to the 13t, right? Yeah. Yeah, so we can just using that, right? So as it is, right? Because this is a Wronskian, we found out, right? So copy, yeah, as it is, yeah, Wronskian. Okay, now, and then K naught, K sub 1, so K naught, I am using K naught is 4, and then K sub 1 is negative 25, right? So 4, negative 25, and then y sub 2, y sub 2. y sub 2. Okay, so let me copy this one, y sub 2 and y sub 2 prime. This one, right? All right. Okay, now 1 over negative e to the negative 13t. We multiply, so we will get negative 28 e to the negative 70 minus plus 25 e to the negative 70, right? Okay, so we simplify inside first, more easier that way. So negative 3 e to the negative 70, right? Then we multiply with outside. So what do you get? So it's a negative 3 and positive 3 and e to the negative 7 minus 13. So you want me to do for you? Negative 70 minus 13, right? Which is the positive. So 3e to the positive 60. Yeah, positive. Yeah. Okay. All right. So let's pick when t equal to 0 because 0 is always easy, right? So pick when t equal to 0, then we have a 3 c sub 1 c sub 1 equal to 3 e to the 3 0. How about just 0 equal to 3, yeah? Okay, now c sub 2. So we are using this format, C sub 2, right? So C sub 2. Okay, so Wronskian, same. We have C sub 2 equal to 1 over negative e to the negative 13. Y sub 1, k not k sub 1. So we have this one, right? So same. Copy. And then y sub 1. Y sub 1 prime, y sub 1, y sub 1 prime, y sub 1, y sub 1 prime. So I want to use this one. Okay. Yeah. Okay. Now, four, right? Oh, I am recording, right? Okay. So multiply. So we have 1 over negative e to the negative 13t and negative 25 e to the negative 6t minus 4, 24, positive 24 e to the negative 6t, yeah? Okay. Now, inside we get negative e to the negative 6t, right? Okay, so we multiply, so we have negative e to the negative 6t minus 13t, which is a positive. So we have 70, yeah. So that would be, wait a minute, it's a positive, right? Yeah. Okay. So positive e to the 70. So once again, when t equal to 0, we have e to the C sub 2? C sub 2 equal to e to the 0, which is 1. Yeah. Okay, now I want to writing nicely. Okay, let me make another page then. So we have the linear combination form, right? So we have y equal to c sub 1, y sub 1 plus c sub 2, y sub 2. So y equal to c sub 1, we have earlier 3. And then y sub 1. What was the y sub 1? Y sub 1 e to the negative 6t given, right? Plus c sub 2, we found 1. And y sub 2, y sub 2. Y sub 2. And y sub 2, where's y sub 2? C sub 1, y sub 2. This is y sub 2, e to the negative 7t given, right? E to the negative 7t, right? Okay. So we knew that c sub 1 equal to 3, where c sub 1 equal to 3, c sub 2 equal to 1, and y sub 1, y sub 1 equal to e to the negative 6t, and y sub 2 equal to e to the negative 7t. Yeah? Normally, we don't write down 1 here, right? Yeah. Okay. Now, the last concept theorem here, then we are done for this section. So let me just read. So theorem, we have Q and R, continuous. This means continuous. Continuous. Yeah. On open interval, and let y sub 1, y sub 2 be solution of, and linear second order, and we have a homogeneous equation, right, on AB. And they say that the following statements are equivalent, yeah, A, B, C, D. Okay, so we have a general solution is y equal to c sub 1, y sub 1 plus c sub 2, y sub 2. We just had that, right? General solution. And y sub 1, y sub 2 is a solution. Yeah. And y sub 1, y sub 2 is linearly independent on AB. So we had that linearly independent from the linear algebra course, and now differential equation. So not multiple of the other. All coefficients are zeros, right? So not multiple of the other means like when we talk about the linear algebra, right? So we have a vector. So multiple of another means stretched most of the time or shrink, right? Yeah. So same shape. So think about the same shape, stretch or shrink. That's linearly dependent, right? All coefficients are zeros means trivial solution, right? Yeah. Okay. Then the last one, the Wronskian of y sub 1, y sub 2 is non-zero. So these four are equivalent, yeah? So we just had that y sub 1, y sub 2 are non-zero, right? So e to the negative 6t and e to the negative 7t, right? Yeah. Okay. And then I said I think c sub c times y sub 1 is also solution. Y sub 1 plus y sub 2 is also solution. Yeah. Any linear combination of y sub 1, y sub 2 also solution. And If Wronskian is equal to 0, then this is linearly dependent. Yeah. Okay. Thank you for watching. See you in the next video. Bye.